In this video tutorial, I'm following the work of a YouTuber who has used the ABAQUS CAE program to solve a spinning disk with axisymmetric shell elements. So what I would like to do is to retrace his steps and do the same problem with the 3D Experience Release 2022x. Uh, this playlist is useful for people who are either novice in 3D experience and they're trying to get into it, or they're transitioning from the ABAQUS CAE into the 3D experience whose native FEA solver is actually the ABAQUS program. The strategy that we have is take videos that are already done in ABAQUS CAE and in a step-by-step fashion and follow the corresponding steps in the 3D experience. Okay, the problem that I'm going to be doing is actually the work of this gentleman, and the reference is given here. And the idea is that you have a disk of a constant thickness. You can think about it in terms of solid geometry that looks like that. And this can be solved as a solid problem. Can be solved as a solid problem, and there are different ways of doing it. Or it can be done as a shell problem, with a given thickness. Or it can be done as with an axisymmetric continuum 2D elements. In other words, you mesh this face, you mesh this cross section with a two-dimensional element and then sweep it around. Alternatively, you can mesh that, create that surface with one-dimensional beam element, which is swept all the way around. So that's not what we're going to do, or that, or that. We are going to be following this process. So basically, we make a one-dimensional beam element and declare them as axisymmetric, essentially shells. That means that it's swept all the way around, and we're going to solve the problem with such elements. Now, the dimensions are given here, and the material properties are standard aluminum. Given there, rotational speed is about 1,000 radians per second, which is roughly 9,500 RPM. And the thickness of this disk is 1 millimeter. We're going to model the cross section exactly like the work of the reference that I showed you. We're going to model it with 10 parabolic beam elements. Now, uh, I have some comments here, but I will wait until we get there, and we'll get back to these slides later on. Okay. Right. So let's go ahead to 3D experience. Because we're going to be doing basically one-dimensional problem, which is axisymmetric in terms of shell element, we're going to go to generative shape design because we're going to have to create a surface. Okay. So on that vertical plane, I will sketch that one-dimensional cross section that eventually is going to be virtually at least rotated around. So I'm going to draw a line here and put the dimensions. So the inside radius of that disk is going to be 20 millimeters. The outside radius is going to be 30 millimeters. So dimension from this point to that axis. This is going to be 30 millimeters. There we are. So essentially we have this line, which is going to be eventually meshed with one-dimensional beam element and then declared as axisymmetric shells, which means virtually it's revolved around 360 degrees. Okay, so that's pretty much it. This is our geometry. We exit, and I'm going to declare, I'm going to create our material properties. So let me go to tools, add and create a material, and I'm going to call it axisymmetric shell, axisymmetric shell video. video. Okay, let's create it. We're going to input the numbers in a few minutes. So right here, Axisymmetric Shell video, right click, apply, and I can close that window and apply it to my part, and check mark, green check mark, and now we're going to input the numbers. So double click on materials simulation, it's structural, general, density, in unit of tons per millimeter cube. That reference uses 2.7 e to the minus 9 tons per millimeter cube. Okay. And then as far as the elasticity constant, you go to ABAQUS multiphysics, mechanical elasticity, elastic 70,000 MPa. This is the Young's modulus for aluminum, and Poisson ratio 0.3. And say OK. We quickly save this. Now, if you watched another video that I have done, which is for axisymmetric model of a thin wall pressure vessel, basically using 2D continuum elements, you see that what we need to do, we have to create, we have to go to the, let's go to that part. We're going to create a geometrical set. So under essential, we're going to create a geometrical set. This is very important, geometrical set. And in it, I'm going to put the origin. Now remember, the axis of rotation of this axisymmetric object is z-axis, right there, okay? And we need to declare an origin, and that origin must go into this geometrical set. It's a must. So a point, notice that it goes into the geometrical set because it's underlined, it's current, and coordinate 0, 0, 0. So there is my point right there. You can see that. Now, I'm also going to create an axis system, and I'm going to use the z-axis of it as the axis of rotation. The alternative is to create 2 points in the geometrical set and create a line in the geometrical set once again, but I'm not going to go that route. I will instead create a point and create an axis system, which is going to be automatically placed at the global origin. I'm going to use its z-axis later on as the axis of rotation of this axisymmetric problem. And I uncheck this current, okay? Say okay, good. Now, I need to create the surface which represent that spinning disk, okay? And in order to do that, that surface should not be in the geometrical set. It should be in the part body. So make sure you go to the part body, right click, and you say define in work object. So whatever I do, including the creation of this surface, is going to be in part body, not in geometrical set. So if you go to these slides, that's where it is. This revolute surface that I'm going to create is going to be in the part body, not in the geometrical set. This is why I selected part body, and then I'm going to revolve it. I'm going to revolve that line. So we are in the part body. We're going to go to revolve the profile, that line, and revolve it about the z-axis. So try to pick the z-axis there and go 360 degrees. 360, 360, and we say okay. These are the steps in order to create this axisymmetric model. It is not as straightforward as one might think, okay? And it's the same with the other video that I've done with axisymmetric pressure vessel, okay? It's a spherical pressure vessel. Okay, now we are done here. As far as the model is concerned, we are done here. Now, make sure you double click on the top level, this slide, double click. Notice that when you do that, you're going to be sent into this action bar, and there is automatic FEM here. So if you go to the slides, you see that That's right. Once again, double click on the top level assembly. This will place you in the model assembly design application, and that's the guy that we want. This guy, okay, which is called automatic FEM, automatic FEM. So let's go back here. We are already there, automatic FEM, and if you look at it, there are many things you can do, but the one that we're interested in, Axisymmetry. You click on it, this dialog box opens up. Okay, it's asking for a plane. It really doesn't matter where this uh, basically line or beam elements are going to lie. And the way I have done it in the YZ plane. Okay, YZ. I think I selected YZ. I'm not sure. Let me actually remove that. Try it again. YZ plane, right? So YZ plane. We can do it from. We can do it from this phase. Let me remove this. Okay, and select the YZ plane. Yeah, YZ plane. YZ plane. Okay, the origin, you have to go and select it either from the screen or from the geometrical set point. If this point was up there in the part body, you would not be able to pick it. And the axis is going to be the Z axis right there. Z axis. Okay, now here you can do it either as basically 2D continuum or 1D beam. Okay, now here, when I select the surface, see that? When I select the surface, immediately this will disappear. This choice will disappear. So I select the surface, just watch all of the stuff down here is going to disappear. Right there, we are left with beam. So what I'm going to do for the mesh size, I'm going to use 0.5 millimeter, and I'm going to use parabolic, and basically these are some uh, information about the mesh size. See, parabolic 0.5. Okay, and let's move back there and say okay. So you will see that when you do that, an abstraction is created. Oh, I forgot something, and that was the thickness of the shell. I forgot to do it. Let me undo this for a second, or actually I don't have to undo it. I can go there and make a thickness 1. Because when I got this window, here, uh, yeah, there was a place for the shell thickness that I I rushed myself and ignored it. There was a 10.83 something there, and it took it as the thickness of the shell. Obviously, I can fix it. What I did, I went and double clicked on this shell section property that was created, and the thickness should be 1 millimeter. Okay, sorry, I should have not closed that window right away. There was a box there which says a shell thickness, and I had to change it to 1. I forgot. There was a value 10.8 there. Okay, that's good. Now, we do have a mesh made of beam element. The properties of the shell is correct. It's going to be 1 millimeter thick. And if you want to see it, let's right click, go visibility manager, and let's say don't show me the part. Don't show me the part. Just show me the mesh. Now, if you don't see it, just say, come here and update. Okay, if you don't see it, just come here and update this thing. Update, there. And if you look closely, you'll see that there are 10 parabolic, actually 20 parabolic beam elements. There are 20 of these, and these are quadratic or parabolic, and there are 20 of them. And if it didn't show on the screen, just go and update the mesh. So if you look at this, one of these slides, it says, yeah, if you don't see it, update it. Okay. Uh, yeah, good. Okay. So let's get back our part. There we are. This is our part. Of course, it shows you the whole thing. I don't want that. I just want Let me uncheck that. Let me uncheck it. Don't show it to me. Okay, fine. All right, let's move on. We are done here, and two abstractions are created. Basically, this is the information that is needed to handle this axisymmetric shell. You don't have to fool around with any of these. So now we're going to go to structural scenario. Select the finite element model that was created, just like before. We're going to go to procedures, which is static analysis, static step. Let's give it an initial time increment of 0.01. This is a simple problem. Actually, even with a smaller number or even with one, it would have worked. But I did change it to 0.01. Okay, and I don't think we're going to exceed that many number of increments. So we just leave it the way it is. By the way, the geometrical nonlinearity has been included here, but again, it really doesn't matter whether you leave it on or off. But I will leave it on because that video reference on using ABAQUS CAE, I think he leaves it on. Okay, good. The next thing is to go to restraints. That entire thing, notice that it says RZ, radial and transverse direction. You click on the fixed displacement, you select that line, and it says does not move in the direction Z. Because this is spinning, it's spinning there, does not move in the direction Z. It's spinning about this axis, right there. And we say, okay, good. As far as the load goes, it's a centrifugal load. It says centrifugal force. You click on it. The whole body is going to be selected. And the RPM, let's actually put that unit that I have 1,000 rad per second, and it's going to automatically convert it to RPM because my unit is there is roughly 9,500 RPM, and we say okay. We don't have to do anything because in axisymmetric problem, rotation is always about the z-axis, the real z-axis. Okay, good. Now, we are pretty much it. This is pretty much it, except that when you go to simulation, let's ask for some information. If you go to that video tutorial for ABAQUS CAE, the same problem is done, you do have to ask for additional information. So stress, but not everything actually. Let's uncheck that. I want the stress components because eventually I want to plot the radial stress and hoop stress. And if you want one meso stress, we can ask for it. One meso comes always with as default, but anyway, I ask for it. So I ask for components of stress components, okay, which are going to be radial and axial and hoop, okay, and we say okay. Let's do a check here. Model check. I should have saved this thing, by the way. That's good. It went through. Actually, let's save it here. Before we do the simulation check. Let's do the simulation check. This is also going to go through. There are some warning messages that, if you want, you can read, but I don't pay too much attention to it, which is a bad idea. But unless the software just bombs out, and then I'm going to start reading. This is a terrible way of doing things, but yeah. It's going to go through. If you watch that video from ABAQUS CAE, you see that all icons are different. Interface is different. But it's the same thing in the background, same software in the background, and with these changes. Okay, there's two warning here. That's okay. I have no problem with it. Let's go run it, which means simulate. We have asked for additional data, and we're going to plot it later on. Okay. These axisymmetric capabilities are very useful because there are quite a few things in real engineering application which are, geometrically speaking, they're axisymmetric. Okay, and doing it with this feature, which was made only available just last year, in the last release, 2021, gives you a very efficient way of solving such problems. Okay, it's almost done. Good. So let me close this. Here's what we have. Here is our, out of the way. Okay, here is our structure. And this is the initial time increment where, of course, everything is zero. If you go to the next time increment, you see that the stress is building up. Finally, one meter stress reaches at 2.19. Okay. Now, if you look at if you want to see this thing better, actually, let me do the following thing. Let me go to the display, and there is this icon here. It says results option. And down here, you can actually make a fake three-dimensional view of these elements. So sweep axisymmetric, go 360 degrees, 360 degrees, not 90. And don't use 10, use more segments so that it's more pleasing. Maybe, I don't know, 20. Let's see how it looks like. Let's make it 50. Okay, so this is a fake view of these virtual one-dimensional element that we use to create an axisymmetric shell, swept around. Now, by the way, if I double click on this and go to the last icon and say, don't show me the icon, show me the mesh 2, and apply, it shows you the fake two-dimensional mesh that was created. These were actually beam elements that were virtually rotated, revolved, to create these fake three-dimensional shell elements. That's what we call axisymmetric shell. There's really not shell elements in the conventional sense. Now, can we plot the other components of stress? For example, sigma 1,1, and so now S11 is going to be the radial one. S22 is going to be the hoop, and S33 will be, of course, 0, which is because this is a shell element, essentially. So, but you can't get it here directly, so what you need to do, you can go to plots, click on the plot, contour plot, and here you're going to check one, not one meses, you want the component, as component 1,1. This is the radial stress, and yeah, so now in problems like that, if you go to a strength of material book or stress analysis book, you see that the radial stress is 0 at the inside, 0 at the outside, and biggest on the in the middle somewhere. So if you say apply, you can see that. Okay, 0 inside, 0 outside, biggest in the middle. And once again, if you want to see the mesh for some reason, you can go there and say, show me the mesh too. It's not a big deal. Apply. Good. Now, say okay. If you want to plot the hoop stress, so once again you click on this icon, contour plot. This time you go and use not one meses, but use sigma 22. Now there's kind of a bug there, so sigma S22 does not show in the initial in the list until you do it again. There we are. Now, hoop stress is going to be biggest at the inside and smallest on the outside, and never 0. Apply, and actually it's going to be very close to the 1 meter stress because the radial stress is almost 0. So these are things that are done in that video tutorial, but they have done more. So they were going to plot, they have done the plot of these stresses uh, as a function of going from inside to the outside, okay? Not as a contour. So we say, okay, leave this thing here. That requires creation of a path. Now, first thing I'm going to do, I'm going to go back to my display and get rid of this. So I don't want to do it like that. Very good. Close. Okay. All right. So you go to plots. Actually, let's go to setup. This is where you create a path. See that? Let me zoom in first. I want to plot the stuff as I go from the inside to the outside of the object. So this requires creating a path, and I'm going to do it by taking 2 points. I'm doing basing on 2 points. Okay, this point, which has coordinate almost 20 and 0, and that point. The path is going to be constructed going from this point to that point from 20 to 30 millimeters. You say, okay? And this is path number 1. You can see that path number 1. And you can create, I mean, there's no way I can create another path here. This is one-dimensional problem. This is the only thing that I can do. You say, okay. Now we go to the plots, and over here it says XY plot from path. You click on it, and this thing pops up. So I want to show you where we are with respect to the slides. We are right here, okay? Path, XY plot from a path, okay? So let's see now, we go there. First of all, it's path number 1. There's only one path that I have. True distance from inside to the outside. So it's going to be 0 to 10 because the inside to outside, the difference is 30 minus 20, which is 10 millimeter. And check the intersection. That'll give you everything in the middle. Okay, more points in the middle. Let's do that. So you go down here. This is stress component 2, 2. So this is the hoop stress. Okay, hoop stress, and then say apply. It created it, but it's up here, right there, right there. Okay, this is the hoop stress. Biggest on the inside, smallest on the outside. Never 0. 2.19 all the way down to something. Let's do another one. Let's do another XY plot from path. I really didn't mean to close that. I should have kept that, but that's okay. We just move this thing on this side. Okay. So this time we're going to do S11. S11. Again, intersection. And apply. Now that plot is here, but I have to get it. Where is this? My plot is somewhere here. Let me see. It's not there. Let's see how many plots I've got there. It's somewhere there. Actually, under results. Let's make sure I should have 2 of them. Right. And we say, I'll say close. Okay, no problem. Right there. You can see that. Okay. So this is the radial stress. This is the hoop stress. And these are the graphs that are generated in that video tutorial using the ABAQUS CAE. But he's doing more. He's saying, actually, can I send this information to an Excel spreadsheet? So I put the cursor there, right click, export. So the first one is I believe that was the radial one. So export, and I'm going to use Excel workbook, okay? And yeah, so you can give it a different name if you want, but anyway, you say okay. So what happens is an Excel spreadsheet is going to open up, and the information as a function of radius all the way from distance from 0 to 10 millimeter is given, and these are the hoop stresses. Yeah, this is the hoop stress, 2.19, etc. So let's keep this thing here. Now let's do another one. So we go to the other one, right click, export. Now here, yeah, through Excel workbook, say okay. It's going to pop up in the other one. This was the radial one. Where's the other one? Oh, this is the, sorry, this is the radial one. The other one is the hoop. So if you want, you can, for example, copy these things. They give you two separate Excel spreadsheet, one for radial, the other one for hoop. Home copy, and you can go to the other one, to the other spreadsheet, which was right there. And if you want, you can add it. Home paste. Yeah. So you have the same information which was given in terms of these two curves in the form of Excel spreadsheet. You can do all kind of fancy post-processing with it. Okay, so the guy in that tutorial in ABAQUS CAE also shows you how to export these into an Excel spreadsheet. But believe me, interface different, icons different. It's, you know, requires some practice, and really that is the purpose of these video tutorials. That's why the playlist is called Transitioning to 3D Experience from ABAQUS CAE, from ABAQUS. All right, good luck.